This is assignment 5, review for midterm. So the key topics, I think we have insertion sort, merge sort, proof of induction, heap sort, time complexity, including the master theorem, substitution to find the time complexity or running time. We also have linear time sorting, including counting sort, radix sort, and bucket sort. And here I provide 5 questions and the solutions. So let's see, next slide. The first one is use master theorem and tight symplectic bounds. Find tight symplectic bounds for the following recurrence. And this is the recurrence. Tn equals 3t. In parentheses, we have n divided by 3, then plus n squared. And here we also, or I also provided geometric sequence. That's a to the power of 0 times a to the power of 1 times a to the power of 2 plus etc. until we plus a to the power of n. So this sequence equals 1 minus a to the power of n plus 1 divided by 1 minus a to the power of 1. Okay, so if we use master theorem, then we know a is 3 and b is also 3. And we know Fn equals n squared. While this term, we know n log BA equals n to the power of log 3, that equals n to the power of 1, so that's n. So compare this n squared with, Fn with this n log BA term. We know this Fn is the dominant term, so the time complexity is big theta n squared. So next question is use substitution method to show the solution of Tn equals 3t. This is the same one. Tn equals 3t. In parentheses, we have n divided by 3. Then we plus n squared. And we want to show this solution is the complexity is big O n squared. So Tn, we start with Tn equals 3t n divided by 3 plus n squared. That's equation 1. Then in order to erase these t terms on the right-hand side, we have to multiple. Okay, so let's forget about that. So we have Tn equals 3t n over 3 plus n squared. Then we substitute this n with n divided by 3. So then here equals Tn, n equals by 3 equals 3t n divided by divided by 3 squared, and then plus n squared divided by 3 squared. And the next one, we substitute this Tn with this n in the Tn with n divided by 3 squared. Then Tn divided by 3 squared equals 3t n divided by 3 to the power of 3 plus n squared divided by 3 to the power of 4. So in order to remove these t terms on the right hand side of the equations, so I have to multiply this equation by 3 and then multiply this equation 3 by 3 squared. Okay, so then now we can erase or cancel out this 3t term with this 3t term, and then we divide it by this 3 times 3t term with this 3 squares times this t n divided by 3 squares term. Okay, anyway, so we do this much more equations until we reach t1 equals 0. Okay, so this is k times equation k, and we know k because we divided each of this n by 3. So we know k equals log 3n. Okay, so now we add all these equation up, then we get Tn equals n squared plus n squared divided by 3 plus n squared divided by 3 squared plus etc. until we plus this n squared divided by 3 to the power of k. Then this whole terms equals n squared parentheses. In the parentheses, we have 1 plus 1 over 3 plus 1 over 3 square plus etc. until we plus 1 divided by 3 to the k, power of k. Then we do more steps. Then until we get this 3 divided by 2, and then parentheses. In the parentheses, we have 1 minus 1 divided by 3n. Then we times n squares. So in these whole terms, we can ignore the constant terms, here. So I'm sorry, go back here. We know this time complexity equals big factor n squared. Okay, so next question is order the following functions by growth rate. So we have n squared, we have n log n, we have 2 to the power of n, and then we have n factorials. And we now we first have to compare the first two terms, n squared and n log n. So compare this. Now we know, oh, I'm sorry, here is n squared. Okay, so it's n squared equals n times n, excuse me. Then n log n, we know it equals n times log n. And because if we cancel this n out in these two equations, we have n and log n left. And we know n is greater than log n. So therefore, n squared is greater than n log n. Next, we compare n squared with 2 to the power of n. First, we apply a logarithm on both terms. So n squared becomes log 2 n squared. And 2 to the power of n equals log 2 to the power of n. We know log 2 n squared equals 2 times log 2n. while log 2 to the power of n equals n times log 2. That equals n. Now, we know if n divided by log n times log n, this whole term will be greater than 2 log n when n is greater than 4. So we said if n is greater than 4, then n is greater than n squared. Let me see. If n is greater than 4, then I think here should be n squared. Sorry, n squared will be greater than 2 and minus 2 times log 2n. Let's see, is it true? I'm sorry, no. This is coming from this here. So if n is greater than 4, then n will be greater than 2 log n. And therefore, 2 to the power of n will be greater than n squared when n is greater than 4. Okay. Next one, we're going to compare this 2 to the power of n with n factorial. Again, we apply a logarithm on both terms. So 2 to the power of n equals n log 2, while this n factorial becomes log n factorial. So here, n log 2 equals log 2 plus log 2 plus log 2. So it's an addition of n times of log 2. Then this log n factorial equals log parentheses. In the parentheses, we know is 1 times 2 times 3 until etc. until times n minus 1 times n. And this whole terms equals log 1 plus log 2 plus log 3 and plus log 4, etc. until we plus this log n. Then let's compare the first 4 terms, the summation of the first 4 terms. So the summation of this 4 terms, log 2 plus log 2 plus log 2 plus log 2 equals 4. And here, the first 4 terms, the summation of the first 4 terms of this would be log 1 plus log 2 plus log 3 plus log 4. So we know the sum of these 4 terms equals 4 point something, so which is greater than this 4. So we know we know this n factorial is greater than 2 to the power of n when this n is greater than 4. And therefore, the order of these functions should be n factorial greater than 2 to the power of n greater than n squared greater than n log n. Okay, so question 4. Give the big O of the following code. And here, I need to provide a power sequence or summation of this sequence. So the power summation of 1 square plus 2 square plus 3 square plus etc. plus n, etc. until we plus this n square equals this n parentheses. In parentheses we have n plus 1 times parentheses 2n plus 1 and then over 6. Okay, and the code is here. Sum equals 0. For I equals 1, if I is less than n, then I plus plus, and the colon here. For j equals 0, maybe no colon here, sorry. This should be a bracket. Okay. So for j equals 0, if j is less than I times I, then j plus plus, then sum plus plus. Okay, so here, when I equals 1, we know first, if I equals 0, then this j less than 0, because I times I is 0 times 0. This is 0. J is less than 0. No, this is not true. So we are not going to have any operations. So, but when I equals 1, then we know j equals 0. J is less than 1 plus 1, right? Then we do the summation one time. When j equals 2, when I equals 2, then j equals I can't say j equals 2 square, because it's j, here is j less than 2 times 2. Then we the operational summation will be done by 2 to the power of, 2 squared, so that's 4 times. When I equals 3, then the operation of summation is 3 squared, so that's 9 times. Then we do this until I equals n. Then we know the operation of summation is n squared. So now, when we add all these operation of summations up, we get this. Actually, it should be like kind of like Tn equals this 1 square plus 2 square plus 3 square plus etc. until plus n square. And this sequence, I have given the power sequence. And this equals 1 divided by 6 n parenthesis n plus 1, and then another parenthesis 2n plus 1. So we do more of how do I say, when we do more steps to expand this equation, get 1 divided by 6 parentheses. In the parentheses we have 2n to the power of 3 plus 3n squared plus n. And we know here n to the power of 3 is the dominant term. So big O of the above code is n to the power of 3. Okay, then this one, oops, sorry. I don't know why I'm not able to see the top, sorry. Anyway, this is question 5. And question 5, I didn't see here the title, but I can read that out. Is to show radius short for the elements in an array of 6 numbers, and these 6 numbers are 124, 9, 53, 6,210, 178, and 3. So the n here, I'm sorry, I need to change it. This, we have 6 numbers, so n equals 6 here should be. Okay, so first we consider a 0 to 9 linked list is a cube for the least significant digit for all these 6 numbers, and we try to sort it. So the process is, first we mark these numbers, each of the numbers, by 10 to find the remainder. Then second, we divide the remainder by 1. Okay, so for example, like for 124, first divided, marked 10. When it marked 10, we get remainder 4, right? Then 4 divided by 1 is still 4. So we put this 124 into this linked list, and its index is 4 here. Then 9, the marked by 10, remainder is still 9. 9 divided by 1 is 9. So we put the value of 9 here in the linked list. Its index is 9. Again, so for 53, mark 10, remainder is 3, divided by 1 is 3, so we put it here, 53. And then 6210, mark 10, we get 0. So then divided by 1, still 0, so we put 6210 here in index 0. Then again, so for 178, mark 10, we get remainder 8 divided by 1. So we put this 178 into the index of 8 here. And then 3, we know the mark by 10 is still 3, remainder 3 divided by 1 is 3, so we put value 3 here. So now the new array, after removing the heads of each cube, is 6210, 53, 3, 124, 178, and 9. Then we use this new array and then we do another sorting using 0 to 9 linked list for the second least significant digit. So we do the same way, and then until we get a new array. And I don't know, maybe here is cut out. But anyway, so if you look from this linked list, we know the new array should be 3, 9, and then 62, 10, 124, 53, then 178. Okay, then next slide. The first step we consider to sort the new array from the second step. So now we build another linked list to sort for the third least significant digit. So now we have to mark by 1000 divided by 100. And then the new array from this step, we get 3, 9, 53, 124, 178, and 62, 10. Okay, now to sort the last 4 digits, we have to do another linked list to sort for this 4th least significant digit. Okay, so now we need to multiply by 10,000, then divided by 1,000. Okay, then after we do this, then we will get this result. And then so finally, the order of elements in the sorted array should be 3, and then 9, 53, 124, 178, and 62, 10. Okay, so that is my 5th question and the solution. So that's the end of my presentation. Thank you.